So the last talk of the session is from Alibaba, where we learn about how Alibaba has revamped their vSwitch data path. So this talk will be given by Ye Yang. So Ye has obtained his PhD degree jointly from Institute of Computing Technology and Chinese Academy of Sciences and Sorbonne University. And he's currently a researcher and developer at Alibaba Luoshun Cloud Network Department. And his research areas include software-defined networks, network virtualization, and hardware-software co-design.
So hello everyone, I'm Ye Yang, a research and also the developer engineer in the Alibaba Cloud. Now I'm excited to be here to share with you our latest vSwitch hardware offloading solution, Triton. Yeah. So the first question is, what is Apsara vSwitch? Let me call it AVS for short. So AVS is a key component in the Oculus network virtualization platform that we have presented in SIGCOMM last year. So look at the picture on the left. In Oculus, AVS is per host deployed switching node, and it's mainly engaged in the packet forwarding for the computing instance like VMs and bare metals. But different from the open source vSwitch, like Open vSwitch, that mainly focus on stateless forwarding and portability. AVS has many stateful logic and need to continuously to support emerging cloud services like the traffic mirror and flow log. These advanced products require more actions and table types in AVS, and that's to the evolution for higher performance. Okay, so in the last decade, we have iterated 3 versions of AVS, and the original version is AVS 1.0. It's in fact a collection of kernel modules. Then in AVS 2.0, we unified them as one kernel process and separated the control plane as another process. Then, inspired by the user space acceleration, we also adopted the DBDK to speed up AVS. In the AVS 3.0, we achieved 4 million packets per second and 2 times 25 gigabits per second bandwidth. And for leaving as much host resources as possible to deploying the VMs, we then offload the whole AVS to the SOC CPU cores on the smart NIC. But the result is not good enough. Due to limited power, the CPU cores on the smart NIC are weaker than that on the host. So the software offloading did not improve much performance. And let's see the AVS 3.0 architecture as follows. We can see that some common designs like the SDN-based parser, matching and action, and the decoding of fast pass and slow pass. The slow pass holds a series of rule tables, and the fast pass acts as the flow cache, and benefited by the structured session that we can do stateful packet forwarding on both fast pass and slow pass. And after that, we turned to use the hardware to accelerate AVS. We developed a smart NIC with both SOC and FPGA units. The 2 paths are linked via 2x8 PCIe 4.0 channels. And based on this smart NIC, we deployed a separate path solution. We run the whole AVS in the SOC CPU cores and implemented an independent accelerated data path in the FPGA units. Why do I call it independent data path? Because you can see that we implemented the parser matching and action all in the FPGA unit, and that means the packet can be forwarded on the hardware path without the software participation. But the hardware path can only act as a flow cache to speed up only the connected flows, while the packets of new flows will miss in the hardware matching and be upcalled to the software. So once the software issues the flow entries to the hardware path, the subsequent packets can pass the hardware passes. However, we found 3 issues in the large-scale deployment. The first one is unpredictable performance, because not all the flows can be offloaded to the hardware due to the limited resources. It's easy to understand. Not all actions are suitable to implement it in the FPGA units. So in our statistics, there are nearly half of the VMs having a traffic offloaded ratio less than 50%. So for tenants, the network performance is unpredictable, and it all depends on whether the flows can be offloaded. But on the other hand, from our developers and maintainers, the AVS iteration velocity becomes slower. Because we need to code on both sides, we need to code the software, and we also need to code on the hardware. And the complex interaction between the hardware and the software also brings the burdens on the maintenance. Also the troubleshootings, you can see we get more troubles in the hardware. To resolve the architecture issue in the separate paths, we developed the Triton. Looking at the picture on the left, it has only one unified data path, and that ensures the predictable performance. So in Triton, packet seriously pass the preprocessor in the hardware, and then software processing, and at last the post-processor in the hardware. The software and hardware communicate via the metadata along with the packet. The metadata contains the intermediate processing result of the packet. So we believe in this architecture that we can finally distribute workloads between the hardware and software to achieve both flexibility and performance. Okay, you may say, that sounds good, to be powerful like the hardware and flexible as the software. But the only key point is how to decide which workloads to be offloaded to the hardware and which should be kept on the software. Sorry. Okay. So the principle is that we want the hardware to accelerate software data paths under the promise of flexibility. We divided the packet processing in AVS into 3 stages: the parsing, matching, and action. And then we evaluate the CPU usage on the typical traffic. For parsing, it's mixed, it's fixed, and there are many memory access operations. So the 27% CPU cycles can be saved by totally offload these workloads to the hardware. For packet matching, it is flexible and should be changed with the services. So we keep it in software for rapid iteration. But we can use the hardware to accelerate it as much as possible. For example, we offload the key and flow IDs into the preprocessor, but no actions. Yeah, no actions. So the preprocessor can match packet in the accelerator and get flow ID to be used by software. The software can directly use the flow ID to access the flow structure. And for action execution, the flexible and changeable operations like in cabling header should be kept in software, and our related works can be offloaded into the hardware. Other workloads like drivers, yes, we developed a special driver to cooperate with hardware to save the CPU cycles. That's important. To provide fine-grained statistics, we use pure software to support them. But here now, Triton is not good enough. Though it achieves the flexibility we wanted, but each packet needs to pass by the software AVS, and it may become the new bottleneck. For example, each packet will be DMA'd twice in the PCIe bus, and the physical bandwidth will be wasted. And the CPU processing will slow down the packet rate gained by the hardware acceleration. Okay, for bandwidth, we observed 2 facts. The first one is the bandwidth equals to the packet rate times the packet size. But actually, the useful part is only the payload, not header. And on the other hand, in packet processing, we only care about the packet header, not the payload. So 2 key ideas come out. We can increase the packet size to support jump frame and increase the weight of payload in the single packet. Then we can reduce the useless packet payload moment on the PCIe bandwidth. We can see with the PCIe bandwidth here. But supporting jump frame in cloud scale is not easy. we need to consider many stack VMs and out-of-date infrastructure. So it's quite different from supporting Java frame only inside a specific cluster. So to ensure network connectivity in multi-MTU communication scenarios, we add the MTU into the routing tables as the figure shows. So when AVS needs to send a packet to a VM, it will get a next hop's MTU and compared with the packet. If the packet larger than the MTU, two possible actions will be required. If the don't flag bit is not set in the IP header, the AVS will send a packet to the hardware for fragment. But if the packet has don't flag bit, AVS will drop it and generate an SMP packet to activate the pass MTU discovery in the guest OS. So generating packet is too flexible and not suitable for the FPGA, so we implemented it in the software. Another optimization is header payload slicing. Whenever a packet is received, it will be splitted, and the payload is stored in the block run, and header will be DMA'd to the software. So after software processing, the packet header will be returned to the hardware and reassembled for sending out. However, the biggest question is the block run in the hardware is expensive, and we only had limited buffer in it. So it may run out if AVS process too slow or AVS directly crashes. So we use the timeout mechanism to avoid the buffer leak and use back pressure to reduce the sending rate in the guest OS when the buffer in use exceeds the threshold. The result shows that Java frame plus the header payload slicing reduces more than 80% of the useless data movement and achieves 3 times of bandwidth up to the limitation of hardware ports. Then we come to the packet rate. We also observe that even in the batch processing, the CPU is not efficient because each packet in a batch all require an independent packet matching. But the packet of different flow always arrive in an interleaved manner. So we just began to think, how about supporting vector processing to reduce the matching times and use the hardware to aggregate packet in the same floor? So look at the picture. We compare the batch processing and our vector packet processing. So in batch packet processing, one batch with n packet requires n times the packet matching. And in Triton with vector packet processing, hardware will aggregate the packet in the same floor into a vector and schedule it into the software so that the software can only match once for a vector with n packet. That greatly reduces the CPU cycle in matching stage. The results show that the hardware-assisted vector packet processing greatly increases system performance. We can see that using 8 dedicated SOC CPU cores for AVS, Triton achieves 36% packet rate improvement. So let's see the overall performance. The Triton achieves 2 times in bandwidth and 1.25 times in packet rate than the software pass in separate pass. And we can see it even achieves the comparable performance as the hardware forwarding in the separate pass. For connection establishment rate, the hardware assistance in Triton increased 72% CPS than the separate pass, but the cost is 2.5 microsecond latency increase. That is introduced by the per packet movement on the PCIe bus. And the latency increase is acceptable to us because the latency in the guest OS protocol stack is far more than that. They are all at the millisecond level. So for predictable performance, we conducted an extreme scenario that tenant refreshes the routing table. So we can see in separate paths that when routing table changes, the traffic in the hardware path will go up to the software to update the flow cache. So tenant will experience a long time and huge performance drop. This is also the gap between the hardware and the software. But in Triton, we have only one unified data path. So the performance drop is light, and the tenant will only experience seconds of JIT. So for flexibility and operation, Triton provides much more finer-grained operational tools, like the table shows. And we keep all the service-related logic in the software also ensures the rapid iteration and reduce the development cycle. Then, how do we learn from the deployment? I think it mainly includes below. Using more hardware queues to aggregate packets can save resources and avoid reordering. And the second is always use back pressure to solve the buffer limitation. Then we recommend to postpone the TSO, UFO, and other, the R-related offloading operations of the WhatIO that is on the SmartNIC. It can help achieve higher bandwidth and save the hardware resources to implement them. We believe in Triton. The hardware platform is not important, and the FPGA is not the best choice. The new technology like the ASIC and the DPA are become the new trend. And what we learned from the years of maintaining AVS. The first is that the hardware team should always clarify the boundaries of the hardware capabilities so that we can provide a failover method. And if you establish an independent team to testing, that can guarantee the overall system's quality, both the software and hardware, For live upgrade, the hardware traffic mirror can help to avoid the traffic interruption during the upgrade. And on the SmartNIC, the resources shortage are always become, and the fast and flexible resource scheduling among several hypervisors, the computing hypervisor, network hypervisor, and the storage hypervisor are the key to solve the resource shortage. And data visualization is more important today. The finer grained data you see, and the better you will do. The last is vendors can coordinate with the tenants on the operation and maintenance under some extreme cases that we cannot enter the guest OS to do the recovery procedures. So let's get a conclusion. In Triton, we unify the hardware and the software data passes, and that provides the predictable performance and the flexibility. For Azure, the network performance not drop, we adopted a series of innovations, like the hardware-assisted vector packet processing, and like we support Java frame with the header payload slicing. And that ensures that we achieve the comparable performance as the separate path. And even in the connection establishment, we increased it by 72%. Okay, that's all. Thank you.
Hi, thanks for your great talk. I'm Guan Yuli from Huawei Network Technology Lab. So my question is, Triton consists of 3 parts, preprocessor, post-processor, and the software parts. So my question is, where is the crypto operation or crypto protocols is conducted in Triton? Which part? Because in cloud, the network cloud also needs some specific crypto protocols. So it means crypto protocols needs also not only performance but also flexibility. So where is the crypto operations conducted in Triton?
I think you're asking me how to trade off between the designs. I think it's if we use cyber path, we have 3 data passes, and we have higher up limit performance, but you should ensure the tenant SLA. You should say you can achieve how the PPS, how the bandwidth, but the software passes cannot achieve that performance. So the SLA is not guaranteed. So we think we need to balance the performance and also the programming flexibility, as we should here. We need iterations, and the evolution. The velocity is important. We need to fix bugs and support new features. If we use the hardware, if you use independent hardware passes, we need to code down both sides. That will slow down the velocity, and also the maintenance will be flexible. So we need to trade off both the three issues. I think it's the answer. Yes.
So the question was, where is crypto implemented?
Yeah.
Decryption, is it in software or hardware? Crypto.
Crypto, in crypto and decrypto.
I see. Encryptor, I think it means something like R-related works. I think it should be placed here, for example, in the preprocessor or the post-processor. And the key principle is we need to put I/O and the services unrelated logical. You know, it has nothing to do with services. So if service changes, you do not to modify the logic in hardware. So I think it should place here.
Okay, thank you.
So one quick question is, so like you mentioned the trade-off between the separate path model and this model. I'm wondering, like, how do these trade-offs, like basically, like, is this future-proof? Is this design future-proof? As you increase the scale of the network, like, would you, like, go back to a separate path model, like, where everything is implemented in hardware, or like, is this design more scalable? Like, how do you deal with scalability?
Scalability. I think scalability, you mean the performance? So the first one is the performance. We can achieve comparable performance. And the scalability, the Triton is the acceleration architecture of AVS, and it is distributed deployed. Each host has a Triton or AVS. I think the performance here now is good enough. And in the future, we will also increase them and develop our new generation SmartNIC. And also, and in company, the architecture will change all the time. You will iteration to satisfy the tenant need and to scale. Yes.
Thank you. Let's
Okay.